the last day of what has been an exciting program so far. Our first speaker for today is Dheeraj Nagaraj from Google DeepMind India. Dheeraj works broadly in the area of theoretical machine learning and applied probability. Um he was an undergrad at IIT Madras, and he did his PhD from MIT before joining Google. And today he's going to talk about um, diffusion models and the Poisson midpoint method. So looking forward, Dheeraj.
Thank you. Uh, yeah, so this was originally I intended to have a longer talk, which covers learning and sampling algorithms in the diffusion model, but I decided to make it a bit shorter. I'll still talk about all those things, but give more thing to this one work, which is called Poisson midpoint method. This was joint work done with my intern Sharavanan Kandaswamy, who was a PhD student at Cornell. Um, so let's begin. So diffusion-based methods are very successful. In the classical context, it's used to do Gibbs sampling. So that is, if you have a function f, which maps vectors in Rd to a real number f of x, then you want to sample from pi of x proportional to e to the f of x, okay, over Rd. So this shows up a lot in statistical physics, Bayesian inference, differential privacy, getting, I think even in theoretical computer science to do volume computations and so on. Okay, so what is the most yeah yeah so this is diffusion based methods also give you a Markov chain, but it's designed slightly differently so that it's so in diffusion models what happens is that you're not given f, so you don't have a description of this, you only have samples. So you want to generate more samples given some samples. So that's the difference. Okay. Uh, okay. So if you have this thing called overdamped Langevin dynamics, so this has been considered by physicists everywhere. So you think of F as some kind of a potential energy, and gradient of F as force. Okay. And then this Brownian motion models the random movements which through unmodeled forces, through unmodeled collisions and so on. Okay. So, but this also is very useful in the mathematical context of sampling from this kind of distribution. If you write this kind of a stochastic differential equation, that would eventually converge to the stationary distribution, which is e to the minus f of x. Okay, so there's also things which are second order in some sense, because there's a velocity, and the velocity accelerates with this force rather than just the position evolving like this, right? So this is known to converge faster. This is called underdamped Langevin dynamics. This is called overdamped Langevin dynamics based on the physics literature. Okay, so if you look at this, I'm not sure if this is clear. This looks like gradient descent. If you look at this, if you ignore this Brownian motion, this is gradient descent. But gradient descent, I want to assure you, is fundamentally different from what is happening here. If you look at gradient descent, there's this just one trajectory which goes to the local minima. And if you look at Langevin dynamics, it just doesn't sit anywhere. It just keeps on going. It's a very rough path. It's not even smooth. It goes all around the place. It's because this Brownian motion increments are very, very large at when t is small, right? When small durations of time. But drift kind of starts dominating at large time scales. So because of this trade-off, you get a sampling algorithm. Okay. Yeah. In this case, but I'll come to diffusion models where it is not known ahead of time, right? So you have to learn it. Okay, so now these are ever more relevant because of denoising diffusion models. Okay, so for example, this is the paper from the paper, stable diffusion XL, right? So basically, you have this immense number of images, so billions of images with captions. So what they do is you give a new caption and it will generate an image which confirms the caption, but it's not to be found in the data set, right? So for example, this person does not exist probably. So if you look at the internet, except for this one generation, this cup of coffee is not a picture, it just generated by the image. So you're given a set of images, you want to do generative modeling through diffusion processes and generate more images of this sort. Okay. So this, of course, has been not just images, this has been applied for videos. This is applied for planning problems. So basically, you want to do constraint sampling. So you want to generate structure of molecules you have a corpus of 200,000 molecules or something. There's a data set, okay, so called QM9, and that gives you, okay, so these are there's a carbon atom here, there's a hydrogen atom here, and so on. These are the bonds, these are their spatial positions, and then it's a distribution of things, right? So now, can you sample a random molecule because of this, which has valid positions, like quantum mechanically valid positions? So again, this is making inroads into that field as well. So it's need not be just this. It could be any distribution we want to generate. We have samples, we want to model it, and we want to generate more of it. Okay. So yeah, so let me just take the prototypical example of image generation, which is where this comes in. So how do denoising diffusion models work? Uh, so right. So initially you have a destructive process. You start with this nice picture of a bicycle here. Okay. So and then slowly add noise with something called the OU process. Okay. So you eventually end up with pure white noise, which has no information about what you started with. Right. So okay, so you look at this stochastic differential equation, it's like dxt is equal to minus xt dt plus root 2 dbt. Right, so what does it mean? So minus xt dt, yeah, correct. So you can encode a image as an RD vector. So you flatten it, for example. Okay, so minus xt dt is it's trying to forget. Yeah, so initial works in 2020, 2019 and all did this. It's called pixel space diffusion. But now they do something called latent space diffusion. So you get a latent encoding of the image, and then you do it on this latent space, and then you decode it. Yes, yes, exactly. So it allows you to do bigger picture. So if you want to do high quality generation, it will be 1,000 pixel by 1,000 pixel, right? So it's a 100,000 million dimension image, which is very hard. Sorry? It's a Brownian motion. So Brownian motion is a function. So it's a random function. It's given ahead of, let's think of an instance of Brownian motion given ahead of time. You solve this stochastic differential equation. It's not a differentiable function. It's a continuous function. So that's why you can't write it as b prime t dt. So yeah. So Ito's calculus develops how to integrate these things and so on. Okay. Yeah, it is a damped diffusion. So specifically, it's a on-scene process. So if it goes too far close to infinity, it kind of drives it back to zero. So it tries to forget where it was, and this part is actually adds noise. Okay, so right. So as you can see, it's slowly forgetting this using this minus xt, and this is noise being added by Brownian motion. So okay. So now the idea is what is the denoising in DDPM? So it is the constructive process. Okay, so if you have a stochastic differential equation, you can time reverse it. So you can run the clock in the reverse time, and it looks like another stochastic differential equation, right? And that stochastic differential equation is given by this one. So it's actually, you can show this using something called the Fokker-Planck equation, but I won't go to that. Let's just assume that this is true. What is PT? PT is the density function of the distribution of xt at time t of the forward process, right? So if you can learn this thing called the score function, you can run this stochastic differential equation in the reverse direction, and then you start with pure noise, and then you sample an image out of it, a new image which is now hopefully not present in the data set. Okay, so what do you want to do on a high level? You want to learn the score function, grad log pt via Tweedy's formula. I'll explain what Tweedy's formula is in the next slide. Yeah. Yeah, so here is time 0, here is time capital T. Yeah, yeah. Okay, so let me be more clear here. So this is, let's say, time 0, and this is time capital T. Okay, so Brownian motion is, let's say, it's a filtration, so that it's measurable with respect to this filtration. So this Brownian motion is not this Brownian motion. It's a new Brownian motion, which kind of filtration goes like T minus T. So you start this again at time 0, but with a fresh Brownian motion, but then you would learn this function at time T minus T. So this corresponds to T minus T of the forward process. Okay. So mhm. 0 to capital T, yeah. So T, if it's like 5 or 6, it's already kind of, yeah, here, you mean. Yeah. At time, right, so no. So in the forward process, I'm going from time 0 to T. In the reverse process, I'm going from time T to 0. I just reparameterize time so that it's this Brownian motion is kind of filtered, right? So that's the, yeah. Yeah, let's say, okay, mixing time of this OU process is very, very well understood. It's like order 1. So if you take a big T to be 5 or 6, it's fine in continuous time, yeah. But you have to discretize this to actually implement this. So as in like 1,000 discretization steps or something like that. So yeah, that's again experimental. So that's one of the things I'll be talking about today. So how to discretize, how much to discretize, and so on. Please. No, this is originally studied by physicists, but it's also central to stochastic calculus. Second one, yeah, you can derive it. It's a classical result known since the 70s, I think, 70s or 80s. This can be derived using Fokker-Planck equation, but it actually has been used because it's very hard to estimate these quantities. So again, Tweedy's formula came out recent. I mean, it has been known, but it was used for inference like this now. And the scale of doing these things was impossible even 10 years ago, right? So even the basic diffusion model training was very hard. And plus also there's this thing about communication between different fields. Computer scientists who look at this were not very familiar with stochastic calculus. Okay. No, the entropy would be here. This is energy. Yeah. So this tries to take you to the mode of the distribution, and this tries to take you away from the mode. So you kind of it tries to take you to a local minima in some sense. If you ignore this t dependence, and this tries to give you some randomness, so it gives you a distribution. So if you actually, there's a theory called Wasserstein gradient flows where you look at these as flows in the space of distributions. So there, this would be like an energy term. This would be like an entropy term. So yeah. So okay. Okay, so finally, if you want to implement this, for what do you need to do? First, you need to know this thing called the score function. This is called a score function. Okay, so let's do that. Okay, so let's just take this destructive process. Okay, so how do you construct time t? It turns out that using Ito's lemma, you can integrate this thing exactly. Okay, so at time t, what is the distribution of xt? It is e to the minus t x naught. So you start with an image x naught, and then you forget it by e to the minus t, and you add this much amount of a Gaussian noise. Right. So as t tends to infinity, it exponentially converges to like just a pure Gaussian noise. Right. So this is equality in distribution. It's not equality almost surely. So let me be very careful with that. Okay. So now what does Tweedy's formula say? It says that if you take xt minus e to the minus t x naught divided by 1 minus e to the minus 2t, okay, and conditional expectation with respect to xt, that gives you grad log pt of xt. Okay, so how did this come up? This is basically integration by parts. So if you write down the expression for this thing, you do integration by parts and you get this equality. So this is the fundamental thing. This was also known since I think 90s, since Tweedy's work, right? Tweedy's formula has been known. Okay, okay, so we have a unbiased estimator for this. So you want to get, like everything you do in deep learning, you want to get a neural network to learn this. Okay, so let's take samples. So you have sample of images x0 to x01 to x0n. They're pure images. Okay, we use the formula to get noise at time t, noised image at time t. We're using Alston-Uhlenbeck process. So that is xt1 to xtn. Okay, so now what do you want to learn? You want to learn gradient. So you have a neural network NN, which takes input as time and xti, the noised image, and it tries to reconstruct xt minus e to the minus t x naught divided by 1 minus e to the minus 2t, right? So it in essence, okay, xt is already known, right? It's already in the input of the neural network. So what it is essentially trying to do is it is trying to learn what is this x naught, expect or conditional expectation of x naught, given xt. So how should I, what is like expected value of a denoised image if this is my current noise? So that is what it is learning. So okay, so you fit a neural network, you use your favorite optimization algorithm to learn this loss, and you have a learned neural network. Okay, okay. So now we this process of learning is called score matching, and let's assume from now that we can do this score matching, and we have a drift function. How do, now my next question, which will cover the rest of the talk, is okay, we know the drift function. How do you implement the stochastic differential equation algorithmically so that it's efficient and you get samples very quickly? Okay, so if you have a drift function b, which we have learned, let's say it's a neural network drift function, which you have learned, it's dependent on time, it is dependent on iterate. Okay, so and then we want to do something called Euler-Maruyama discretization. This is the simplest thing, the first thing you learn in stochastic differential equations. So it would be of the form xt plus 1 is equal to xt plus some time discretization eta, b eta t time of xt plus root 2 eta zt. Okay, so eta is assumed to be very small. It's like, let's say 10 to the minus 3, 10 to the minus 4 or something. Okay, so okay, so I want to explain to you some things about the scaling here. So drift gets a scaling of eta, and diffusion term, this is a discretization of the Brownian motion. So that gets a coefficient of square root eta, because locally Brownian motion scales as square root eta. It's not a differentiable function. It's very rough. It's continuous but not differentiable. Okay, so that's why we have this kind of a scaling. So this gives very, very good performance in image generation when step size is very small. Yeah. Because it's assumed to be like, for example, if you see here, this is like physical time in the sense that it's the continuum time, but this is the iteration number. So you've learned it for the continuous time, but you're discretizing arbitrarily. So you need to kind of make them. Yeah. Yes, so there are several ways. So one is showing it to people, doing like go do a survey among people. Okay, do you prefer this or that? That's a gold standard. But usually there are proxy metrics like FID, pressure inception distance. Yeah, you do get bad images. Yeah. So yeah, there are ways of doing this better. So okay, so this achieves the best performance when the step size is very, very small, right? So, but quality degrades rapidly when step size is increased even a little bit. So I'll show you some pictures towards the end of the talk, how it degrades suddenly, okay? So there is something called RK type methods, which have been used in financial mathematics and physics for a long time. But RK methods, the disadvantage is that it kind of wants you to have smoothness of this drift function and use higher order derivatives, right? Yeah. Yeah. Right. So it's very important. Yeah. So it has to converge to the right value. Yeah. Enough samples and you learn it, and then you maybe have a test set and see what's the error, and then yeah, that's on my another work which I wanted to present, but there's no time. So there are learning theoretic bounds in this. I can share you some of the papers on this. We're also writing one more paper on that. Actually, it's there are some quite a few open problems there too. So complexity of score matching is kind of being understood right now. There is sampling from this. So again, sampling also has outsized influence because okay, I'll tell you. I think I had a slide here. Oh, maybe I missed it. Yeah. So if you want to get best quality, you need to run this for 1,000 iterations. In the sense that if you discretize time, let's say actual physical time is 0 to 5, you want to discretize it for 1,000 times. And it takes about 1 minute on a A100 GPU for to get the best to run this for 1,000 iterations. So it's a huge waste. If you want to generate thousands or even millions of images, this is very expensive. So if you want to take it to like 10 or 50, you need to do something cleverer that can save you 20x compute in the long run. So, okay. So, okay, so there are these RK type methods which require higher order smoothness, okay, which we cannot have here. We can't go on differentiating a neural network again. It's very expensive to do that because there are billions of parameters and so on, and it cannot fit in the memory as well. So is there something which doesn't use smoothness? It's much more simpler. You just get me a trained model and they do small changes and you get the answer. So that's the kind of thing we're looking at. So can we do better? Okay, so now I'll assume that, okay, this is, I'll take the simplest case of, for exposition, I'll take the simplest case of Langevin, underdamped, overdamped Langevin dynamics, so that I can explain things better, but you will see that you can actually fit in a time dependence here and make this a general drift, and all of these things work out. Okay, okay, so let's think about what is the source of error, what goes wrong when we discretize these kind of continuum objects. The first thing is that you write the instance one, which is the actual Ito's lemma, which gives you the continuous process. So if you're at xt eta, how do you get xt plus 1 times eta? So it's given through this Ito's, Ito integral, right? So basically, this is the definition of the process. So this happens. Okay. Okay. So now, if you have this kind of a equation, so this is the instance two, which is the discretization. So you start at xt eta, but you cannot get xt plus 1 eta because it's not computable. So you get xt plus 1 eta hat, and instead of this integral, you replace it by the initial point, right? So this is called Euler-Maruyama discretization, like I said. Okay, so this can be written as error plus what you actually wanted here. Okay, so error is basically the initial point minus the integral. Okay, so let's now think like statisticians. Okay, so and say, okay, can we distinguish between instance one and instance two? And for that, let's have a caricature. Okay, we have this error, and error has a non-zero expectation. So it's kind of a biased approximation for the stochastic integral. It's not a stochastic integral, it's just a normal integral. Okay, so the first hypothesis we have is that we are given a Brownian motion increment. Okay, second hypothesis we have is that it's a Brownian increment plus some constant vector eta times epsilon. So we model the error as some constant vector which is biased. So if you go back to the previous slide. So here this can be seen as Ito process being driven by Brownian motion. This can be seen as Ito process being driven by some other non-Brownian type motion. So if we can distinguish between those, then they're bad. If we cannot distinguish between those, it's good. Okay, so that's the view we take. Okay, so let's see that it models error. So like I said, the discretization is good if we cannot distinguish between these two hypotheses. Okay, so let's, this is a Gaussian, this is a constant. So we can, of course, calculate the KL divergence between these two hypotheses. So it turns out it is order eta times epsilon squared. It's kind of simple to compute. Okay, so for those of you who don't know what KL divergence is, it's a measure of how different two distributions are. If two distributions have large KL divergence, then there are statistical tests which help us distinguish them. And if they're very close, then there is no statistical test which can help us distinguish. Yes, because I'll do another caricature which will tell us what algorithm to write. Okay. Okay. So, right. So now this was the first instance. So second instance, I'll take the another caricature. So H0 is that this is Brownian, and H1 is that it's eta epsilon times Z, where Z is a standard Gaussian random variable. So the amount of magnitude of noise I'm adding in both the cases is the same. It's just that this is zero mean and it's Gaussian shaped. And now if I look at the KL, it is eta square epsilon to the 4, right? It's quadratically better. Okay, when eta we imagine is very small, so this is an order of magnitude better. So, the thing is, if you have two Gaussians of different mean, they're easy to distinguish. But if you have two Gaussians of same mean but slightly different variance, they're very hard to distinguish. So that is the take-home message here. And this will also give us an idea to do an algorithm, write an algorithm which can perform better. Okay, so we want to, the idea is we want to trade off bias for variance, because variance was okay, but bias was bad. Okay, so let's see. So the idea is to make approximation error mean close to 0 while we inject some randomness to it. So this was exactly the idea of randomized midpoint method by Shen et al. In 2019. Okay, so here is a simple idea there. Okay, so you have time t eta. T eta is the natural time, okay, of the continuous process, and there's a time t plus 1 eta, and you pick a random midpoint t eta plus u. So this is u is a random variable between these two. Okay, and then you compute grad f of x t eta plus u. Okay, so I mean, in an ideal world, you will just use this as a drift, but you can't compute because it's a chicken and egg problem, right? You want to compute future times, but for that, if you also need future time, it's not possible. So you do something I call chicken and approximate egg, where you do an Euler-Maruyama discretization and just plug it in at this random time. Okay, right. So the algorithm is this. Okay, you take u to be uniformly at random from 0 to eta, and x hat eta t plus u. This is the Euler-Maruyama discretization to get the midpoint, random midpoint, and this is the algorithm. So you actually evaluate the gradient not at the initial point, but at the random midpoint. Okay, and you see that this is approximately unbiased because if you take expectation only over u, what happens is that this gives you this kind of an integral because you took it uniformly, and this is approximately equal to the actual integral in the Ito definition of the SDE. Right? So this is approximately unbiased, or we can hope that this has less bias than before. Yeah, what did I mention? Yeah, everything works out. I even have guarantees not for diffusion models, but for Longeon dynamics, but we have experiments for diffusion models which also work. Okay, so this is low bias, but adds variance. Okay, so okay, of course, this is a classic result, classic as in 2019, but that's classic in machine learning. So it's a quadratic improvement in strong log concave sampling, and it's hard to analyze beyond this case because of very intricate probabilistic dependence which develops between the Brownian motion and the parameter randomized midpoint. Okay, so recent work also extend this with very deep results or to logarithmic Sobolev inequalities, but only for overdamped Longeon dynamics. So beyond a few very small cases, it's not known how this method works. Okay, so diffusion models like denoising diffusion models are even more complex. They have time dependency. They don't converge to stationarity and so on. So is there a way to extend it to these kind of situations? Okay, so that's why we introduce something called the Poisson midpoint method. This is our work, and so again, this is a variant of that, but this gives you a much better way to handle the dependencies which come up with this discretization. So the idea is simple. Okay, so you approximate k steps of our Euler-Maruyama discretization with step size eta over k, with one step of step size eta, right? So like I said, if you have a very small step size like eta over k, it's very good. So why do you want to approximate continuum? We'll just approximate something with very small step size with one step of our algorithm. Okay, so for now, let's look at this general. So we've completely transitioned to the discrete dynamical system world. Okay, so let's get rid of the continuous notation and think of this dynamical system. Okay, xt plus 1 is equal to a eta xt, g eta, these are all matrices, b eta t times comma xt, gamma eta times zt. Okay, so this covers a lot of the cases, all the cases I've mentioned so far. So this is like a what do you call consistency condition. What it says is that if you use a constant drift, okay, so then if you use discretization, all the discretizations give you the same result. So for constant drift. So this is satisfied by almost every discretization scheme, which I know. Okay, so very general, encompasses all these things I've discussed. Okay, okay. So now let's look at the small step size dynamic. So I won't deal with the general case because it's very hard to parse those equations. I'll just go to the overdamped Langevin case. So if you have this small step size, then the dynamics looks like this. So you replace eta with eta over k, and this is the dynamics. Okay, so now the large step size one can be written in similar form. Okay, so what's the difference here? The difference is that you're using stale values of the drift. So here you're using xtk plus I, here using xtk. So it's a very old value, and this old value is what's causing us the problem. Okay. So our algorithm gives you a bias correction. So we basically add this term. Okay. So basically we pick htk plus I to be a Bernoulli random variable with Bernoulli 1 over k. Okay, and then we add eta htk plus I grad f of x tilde tk minus grad x tilde hat tk plus I. So this is an estimate for the midpoint, and this is the difference between the current point and the midpoint, and the initial point and the midpoint, and this will in expectation cancel out the bias. Okay, so this we call bias correction. Huh? Because if you put its mean value, you will have to do the computation. It's rarely 1. So you have to do this computation only if it's not 1. Okay, you're trying to save on compute, right? So yeah. Okay, so this lowers the bias. Okay, and we can obtain x tilde tk plus 1, x tilde t plus 1k from x tilde tk with just 2 function evaluations by unrolling the recursion. Because this is sparse, only x in expectation only one h tk is 1, others are all 0, right? So right, so it saves us on compute. So like I said, this approximates k steps of with step size eta over k with 1 step of step size eta. Okay. Yeah, that's what I'm going to analyze. So extra noise, we'll approximate it with a Gaussian somehow quantitatively and show that the contribution of that is much lower than the benefit we are getting. Okay, so how do we analyze this algorithm? I already gave you a hint of sorts. So which is that we have a bias variance. So a bias variance decomposition, bias Gaussians were bad, variance pure variance Gaussians were good. So okay, let's do the same bias variance like decomposition. So this is our dynamics. So this dynamics, the extra bias correction can be absorbed into the Brownian motion increments, right? So we can cook up a new process called Z tilde process. Okay, so by absorbing this into this. So we can write Z tilde tk plus I is ZTK plus I. This is original Gaussian, and there is BTK plus I, okay, and VTK plus I, where BTK is called the bias and VTK is the variance. Bias has non-zero mean, variance has 0 mean. Okay? And the thing is, this sequence is not Gaussian and it's not IID. Okay, the dependence comes up because of these things, and non-Gaussianity also comes up because of these things. Okay, so now let's compare these trajectories. So we use the data processing inequality, which says that if z tilde tau for tau less than or equal to t are approximately IID Gaussian, then the trajectories are close. More precisely, the KL divergence between the trajectory of Poisson midpoint method to that of Langevin dynamics with small step size is less than or equal to KL divergence between the noise which is driving these two dynamical systems. Okay, this is data processing inequality. Okay, so that gives us a simple idea as to how to do this. You just prove that this relative entropy between the new fancy process to the old process is very small, and then you have your convergence result. Okay, so what is stopping us from easily doing that? Okay, with this Z tilde is not Gaussian. Okay, so how do you control non-Gaussianity? It's using something called central limit theorem. Okay, so specifically we'll be using this recent central limit theorem by Alexei called in the Wasserstein 2 distance. Okay, I'll say recent for work in 2016 because it's in probability, which is considered recent in probability literature. So okay, so and this does not have correct mean, but two Gaussians without the correct mean, they can be controlled. We know the exact KL divergence once you control for Gaussianity. And the next one is that they don't have the correct variance. This again can be controlled by the formula for KL divergence between Gaussians. Okay. The main technical details here is something called the information transportation inequality, which I'll skip over in this talk. But basically for Gaussians, it controls Wasserstein distances with KL divergence. And we also prove something called a reverse T2 type inequality, where approximately you can control a KL divergence using a Wasserstein 2 distance. Right. So these are important technical concepts which I won't go into in this talk. Okay. So let me give us a short exposition into what the central limit theorem is. So in statistics, this is the most important object of study, or rather very, very important. So What it says is that if you have IID random variables, x1 to xn, which have zero mean, right? And they have covariance sigma, right? It's a random vector. And then if you write x1 to sum of x1 to x1 and divide it by root n, this looks like a Gaussian random variable of with mean zero and variance covariance sigma, right? So you might ask why is Gaussians everywhere? Why do statisticians model everything as Gaussians? It's because of the central limit theorem, right? So if you have a lot of things influencing something, then it starts looking like a Gaussian. Things cancel out, and it starts looking like a Gaussian. Okay, so this result originally, I think, by Kolmogorov, the full version of this was full of it's asymptotic, right? In the sense that you don't know how close it is to a Gaussian. You just know that if you have n tends to infinity, it's Gaussian. So people thought, okay, we need some quantitative bounds. We need to be able to quantify how Gaussian something is, right? So that's why this is called Berry-Esseen type bounds. Berry-Esseen type bounds work best in one dimension. Higher dimension, it's bad. But there's a recent breakthrough in high dimensional central limit theorems by Alex Zai in 2016. So there's something called the Earth movers distance or the Wasserstein distance. Okay, so Earth movers distance shows that how much work you have to do to change the shape of something to something else. So in this case, how much work do you have to do to change the shape of this distribution to make it look like the density of a Gaussian, which is like a pile? Okay, so this is called so if you look at the Wasserstein distance, then we can show that Alex Zai showed that this is of the order d beta square over n. Okay, so d is the dimension and n is the number of samples, and beta is an absolute upper bound on x1 to xn. That is, x1 to xn has density, sorry, has value less than or equal to beta in norm almost surely. Okay, bounded random variables. Yeah, I think so. We can do it for light tails because you can just add an indicator that xi less than or equal to beta, and then rest of it converges to zero because it's very rare that it exceeds something. So Wasserstein distance gives us those possibilities, right? So, and has to scale linearly with them. But as we see, beta would save us here because the amount of noise we are adding to Gaussian small perturbation is very much smaller. Yeah, please. No, actually, beta square is kind of like larger than trace of sigma. It has to be. So, right. So, So in our work, what we do is we have this Wasserstein CLT for Z plus V versus root of I plus sigma times Z. So V was the variance, okay, which is of a much smaller magnitude because Brownian motion scales as root eta, and then the drift scales as eta. So it's a much smaller magnitude of this. So we use the lemmas in Alex Zai's paper, which is the main lemma, which compares small perturbations of Gaussians to a Gaussian of larger variance, covariance. Yeah, please. Mm-hmm. Yeah, it's not. It won't work in the cases which you usually encounter in what do you call it, compressive sensing type thing. So this is not something which would work. Yeah, that's a natural position there, but here you assume that you have more than the dimension. So if you want to do like, okay, if you have sparse linear regression, that's not possible. But if you do like normal L2 regularized linear regression, you usually assume that n is much larger than d. So, okay, so again, coming back to this, so it's a small perturbation of Gaussian. So we get a very sharp bound here. It's hard to parse those results. I won't bore you with the thing. I refer to my paper to get the exact results here. Yeah, this one. That I don't know actually. For law of large numbers, if you have, I mean, you can get a weak law of large numbers very easily by just using variance computation, right? Yeah, sorry. Yeah. Right. For law of large numbers, I guess you'll have to replace root n by n because this sequence will not converge anywhere with a classical result. It only converges in distribution, but not almost surely, or in probability, right? Yeah, 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 right, in Wasserstein sense, right. If it's a Gaussian process, I can see how, because it's very nice. Uh, the proof goes through something called transport inequalities, right? So T2 type transport inequalities, Talleyrand's T2, which has been established for Gaussians, and but it's very hard to establish for general distributions. So if you have those kind of distributions, it might work. But if you want to specifically show that your process converges to a Gaussian process, this might be very good technology for that. Yeah, it's about 9 years old. Yeah, so it's one of the first results I've seen of this kind, because usually if you want to prove high dimensional CLT, it suffers from a curse of dimension. So you take one convex set, what is the probability of this convex set, and you take another convex, same thing under two different measures, and you try to measure the discrepancy between those, and you end up with dimension dependent 2 to the D kind of factors. And you can't do much better there. But this is a very clean result because you're using like a metric here. And, okay, so the main theorem is this. Okay, so I showed you bias variance decomposition. B is bias and V is variance. We say that, okay, at time tk, if you run it till time tk, so capital Tk, say, so KL divergence between these two distribution, the Poisson midpoint method and the very small step size Langevin dynamics is less than or equal to this quantity. Okay, so it depends on bias squared, of course, and then variance to the 4 and lower order terms. Okay. So as you can see, variance, if your variance is large, it's okay because it's to the power 4. But if bias is large, it's squared, so it's really bad. Okay. This is roughly not exactly. There are some technical details I've glossed over. One thing is that there are no mixing assumptions. There is no smoothness assumptions. It's just that the dynamics have to exist. So that's all it takes. Okay. And it makes a very general point, that is, if the dynamics with step size eta over k converges really fast, okay, then Poisson midpoint method also converges fast. Okay, this is just a lot of summations here, but I'll actually substitute numbers there and tell you for what algorithms what happens. So in for this overdamped Langevin dynamics, when grad f is L Lipschitz, that is the smoothness assumption. Okay, so we have KL divergence between xt tilde and xt to be eta to the 4 k d square t. So okay, and here still we have not assumed anything about mixing. Okay, this is just a thing which uses regularity of f's. And for underdamped Langevin dynamics, it's k eta to the 7 t square over gamma. I understand that it's still confusing, but I'll give you the mixing bounds in a very special case. There is something called isoperimetry conditions called logarithmic Sobolev inequalities. Okay, so this kind of shows that your dynamic kind of mixes. KL divergence contracts across Langevin dynamics, right? So under these assumptions, we know that overdamped Langevin dynamics converges with this rate. So xt, which is step size eta over k, that to the stationary distribution pi, the KL divergence is eta d over k eta. Okay, and then our results show that KL between x tilde, that is our approximation to xt, is eta to the 4k d square over t. Okay, this is a celebrated result by Vempala and Vibisano. Okay, so here Poisson midpoint method requires time and number of iterations, right, to be d to the 3/4 divided by epsilon lambda to the 3/4 to get total variation distance within epsilon of the stationary distribution. But Euler-Maruyama, the best known bounds require d over epsilon square lambda square, where lambda is like a condition number. Okay, yeah, yeah, it's this. Yeah. Right. So, yeah, I think this should be root d. Yeah, this could be. I don't know if this can be improved, but I think this should be root d. I'm still working on it. Maybe it's an algorithmic thing or an analysis thing, which I don't know. Nitin? So I did read it up. You sent this link to me at some point. So Milstein mainly considers in physical systems. So there's a diffusion coefficient, and diffusion coefficients are even worse for simulation because a slight error in diffusion coefficient causes a root eta type error, right? So mostly it's about correcting that. But here we are blessed with the fact that we don't have a non-trivial diffusion coefficient. It's a constant. So we can do these things with much simpler. Yeah, so I actually look, so multi-level Monte Carlo again, I think it was by your advisor, or no, it was different. Yeah, I think so, right? So that was multi-level method. I did look at it and I tried to get that here, but multi-level method is for Monte Carlo type simulation, right? So I was specifically doing it for generative modeling, where you want to generate one thing, not compute statistics of a distribution. Expectation, yeah. It's very nice for expectation and that, but this one, there's an accept reject version of this called Mala. So Metropolis adjusted Lanzone algorithm. So that is that's called a this is called a low accuracy sampler. It has poly 1 over epsilon type dependence. Those are called high accuracy samplers, which gives you log 1 over epsilon kind of thing. But it's more complicated. You have to add an accept reject step, and usually these things are used. Which is oh, you can get rid of Lipschitzness. Yeah, here also you can get rid of it, but yeah, we didn't consider it. It's just a standard thing. We can consider it to be Helder continuous, for example. Bounds will be slightly different. Similarly, we can consider the underdamped Langevin dynamics. Here too, we get an improvement from 1 over epsilon to 1 over root epsilon, and we also get a improvement in dimension dependence and condition number dependence. Okay. So here's the exciting part, which is diffusion model. Okay. So here are the results for latent diffusion model. So as you can see, this is called the FID score, CLIP FID score. FID score shows you how nice your generation is. So if it's very low, then it's good. It's close to the data set you're generating. If it's very large, then that means that you've gone wrong somewhere. It's not very close at all. Okay. DDPM is the Euler-Maruyama discretization. So you start at, if you have number of neural network calls, so how many times did you have to call the neural network through your discretization process? So if you start look at DDPM at 1,000 discretizations is really nice. So you get an FID score of 2.3. But once you start decreasing it to about 200, it shoots up. So at 50 calls, it's about 30 or something. It's a log scale, right? So it's very bad, right, if you decrease it. And this purple one is Poisson midpoint method. It maintains the same quality as 1,000 iterations up to 50 iterations, 50 neural network calls. So, but actually the difference is between 200 calls and 50. So it can give you a 4x boost in compute while maintaining the quality. Of course, if you take it even smaller, it just shoots up because our assumptions behind our approximation breaks down. But until here, it's actually quite nice. Okay. So why use diffusions at all? Why not use ODE-based methods? So it turns out that a stochastic differential equation is one method, but you can get an equivalent ordinary differential equation which also samples from a trained diffusion model. Okay, it's called DDIM solver. There's called something called DPM solver, which uses numerical methods on top of ODEs. It turns out that they behave much better with fewer number of iterations. But if you have a very large number of iterations, which you have a lot of compute, then diffusion processes, that is DDPM, are just better, right? So as we can see, at 1,000 iterations or 750 iterations, our methods are much better, right? But when you go to like 10 iterations or something, these methods start becoming better, the ODE-based methods. So what we are offering is that when you're close to, let's say, 50 iterations, we maintain the very good quality, but also we are computationally efficient. But maybe when you want to just run it for 10 steps or something, but you're okay with slightly worse image, you're okay better off going with an ordinary differential equation. So yeah. Yeah. Yeah, correct. So this is on something called Celeb data set, I think. Celeb 256. So there is 30,000 distribution of celebrity images. Okay. Yeah, yeah, yeah. Yeah. Yeah, the people have done that, these toy experiments. And usually it's very hard to distinguish these methods based on that. Yeah, yeah, you can do a pretty good job here, even with multimodal distributions. Yeah, if you use Gaussians, sometimes if the learning is perfect, we know that if the neural network learns the score function, if it can do the regression task, then we know that you will get the perfect sample, right? But again, if the things go bad when you don't have perfect learning, because if you take discretization strength to like 0, there are bounds which show that this just works. Mhm. Right. So people have considered something called Levy-Ito model. So there you have these Levy processes with, let's say, with index alpha, which are driven by stable processes, alpha stable processes, which are not Gaussian. So they don't have a variance, right? So they're very, very high, heavy-tailed. And they were able to generate rarer things much better. But there hasn't been much work after that. And there's also this thing called flow matching, which starts from arbitrary distribution. So if you start from a heavy-tailed distribution, maybe it behaves better. But then again, I haven't, it needs to be understood more from those points. Yeah, I'll kind of end the talk here. This is my last slide. And yeah, if you have any questions, I'm happy to take. Yeah, please. Okay, so if you should know this Poisson convergence theorem, right? So if you have Bernoulli random variables, n of them with the probability lambda over n, okay, the sum of them converges to a Poisson of lambda. So we have k things here with probability 1 over k. So if you go and plot where all you get ones and where all you get zeros between 0 and 1, right? So you draw hi from Bernoulli I over k. So you plot hi at with the points which are 1 at on the line between 0 and 1. You can show that it converges to something called a Poisson process with exponential arrival. So that's why I call it um, mhm, mhm. Levy process, yes. And theory, I'm not sure, but there are some experimental results which are known, how to estimate the drift, what is the reversal. And again, if the expectation doesn't exist, how do you do regression? Those are, or second moment doesn't exist, but expectation exists, you can still do regression, I guess. So you get something like, you won't get the heat equation there. You get something kind of like a fractional heat equation or something like that. Uh, yeah, it's known as in, there was a Neurips paper 2 years ago. 20, so their claim is that it gives more diverse. So you can solve inverse problems with this diffusion model. So you start with an image and you, let's say you blank out their eyes and mouth, okay, and ask the diffusion model to just generate something, right? If you ask this regular things like Gaussian things, it will generate the same eyes and the same mouth again and again. There's no diversity. But when they tried the experiments with Levy-Ito type models, it gave you like sometimes blue eyes, sometimes brown eyes. The mouth shapes were also different. Sometimes it was smiling, sometimes it was frowning. So you get more diversity. I guess that could be because of the tail behavior. So yeah, so again, there are also problems there. So one thing is diversity there too. So if you prompt something, let's say some monument in Italy, it will generate the same picture 100 times. You wanted to generate something different. Again, there are many algorithmic things we suspect is leading to this lack of diversity, and we also suspect another suspect is the Gaussian process which is driving it. So research issues, okay. So can we replace this altogether with a flow-based model? So why are we starting with those? So there's something called rectified flows, right? So which will, given any two distributions, it constructs an ODE which connects first to the second. So if you rectify a rectification again, it gives you a straight line path between those two, right? So you start from a point and you go on a straight line depending on the initial point and you end up at the result. So that you need just one function evaluation to get to the final result, because you can arbitrarily discretize a straight line and you'll end up with the right result, right? So, but that process involves you to learn a model and then generate data from the model and learn from the data generated by the model. So it kind of causes model collapse if you learn from your own generations, right? So how do you do two rectification without undergoing model collapse is a very big question according to me. So yeah.
Okay, so if there are no other questions, okay, one final question.
Yeah. No, but this still is, I think, thousands of dimensions. Millions, I don't know. That's I don't think it's very hard to store these things in memory, and then even the architecture to read off these things, that would be very hard, I think. No, I think it's easy, but again, pictures have a lot of redundant features, right? So if you just compress it using some kind of an autoencoder, it will make it like tens of thousands from millions. So that could be easier to. Oh yeah, there are a lot of video models. Again, video you have to model the dependencies between spatial dimensions and also time dimension, right? So that again calls for architectural change and a lot of things. Yeah, they use latent structure there too. There are things which compress videos as well. Oh, the training these frontier models is very hard. I mean, I think you would need about a reasonable model. I would say, okay, let's say you have 8 or 16 800 GPUs and you run it for, let's say, 2 3 weeks. I think you should be able to train it. It could be much harder, but this stable diffusion, I think, is available for free online open source. You can just download it and fine tune it and do experiments on top of it. I think that would be, yeah, that can be done with 1 or 2 GPUs. It's, that okay, I can send you my papers, and rest of it I'll try to find something.
All right, let's thank Dheeraj for a wonderful talk. We'll have a short coffee break for 15 minutes, I believe, and then reconvene at 50 minutes past 10 for Professor Borkar's talk. Thank you. Very nice.
Thank you.